Yesterday we built like the arithmetic skills to be able to evaluate one of these functions. And exponential functions are going to look like this. F of x, which is just another way of saying y, right? F of x is equal to 3 times the quantity of 1/2 raised to the power of x. So this is not, your typical y equals mx plus b. It's a little bit more complicated. And we're going to graph this exponential function for the domain, -2, -1, 0, 1, and 2. Now, domain, are those x values or are those y values? X values. Okay? So what I'm going to do with this little function table here is I'm going to take each of those inputs, I'm going to put them in, and I'm going to evaluate. Okay, whatever I get at the end of that evaluating, what's that going to be? It's my y values, exactly, or my outputs. Okay? So when we're given a domain like this, that means we have a discrete function. Someone with a quiet hand, tell me what a discrete function looks like. Tyler, what does it look like? Yeah, it's just dots on a graph, right? None of the dots are what? Connected. Thank you, Changsy. None of the dots are connected, right? So we're graphing this function at the inputs -2, -1, 0, 1, 2. Nothing in between. No 1.5, no 1 3/4. Just at those 5 inputs, okay? So let's start out with number 2. I'm going to take I said number 2. I'm going to start with -2, okay? I'm going to take -2 and I'm going to plug it in right here for x. So what it is 3 times 1/2 to the power of -2. Looks a lot like the problems that we were doing yesterday, right? So it shouldn't be too bad. If I raise 1/2 to the -2nd power, what do I have to do with that fraction? Take the reciprocal. We flip it around. 2 over 1. We make that exponent positive. What is 2 over 1 squared? 4. And what's 3 times 4? 12. So this first input, -2, gives me an output of positive 12. All right? Now, what do we notice about the y-axis on our graph? Can we plot this point? -2, 12? No, it only goes up to like 7. So let's skip that one. Let's go to the second one. -1. Same thing. I'm going to plug -1 in as my exponent. I'm going to reciprocate my little fraction. Right? 2 over 1 to the first power. What's 2 to the first power? 2. So what's 3 times 2? 6. Can we plot this point? Yeah. -1 on the x. Positive 6 on the y. Boom. There's my first point. -1, positive 6. Next up, I'm going to plug in 0. Everybody with me so far? My bad. Yeah, in the back we good? Okay. If I plug in 0, what's anything to the power of 0 equal to? 1. And what's 3 times 1? 3. What do we notice right away about my 3 outputs so far? Are they getting bigger or are they getting smaller? Christian?
Smaller.
They're getting smaller. How much smaller are they getting?
By 3.
By 3? 12 divided by 3 is 6? They're getting divided by 2, right? Half of 12 is 6. Half of 6 is 3. What do you think my next output's going to be?
A fraction.
A fraction? What fraction?
3 over 2.
3 over 2. Right? This is like what we talked about with geometric sequences. We're going down output by output, and we're taking it and cutting it in half, right? So my, what do we call it? The common ratio? What would my common ratio be here? 1/2, right? If I'm multiplying each output by 1/2, my common ratio, take a look, inside those parentheses is 1/2. Okay, we're going to keep that in mind. We'll talk more about that tomorrow. So let's check this, make sure we're right. If I plug in 1 for my exponent, what's 1/2 to the first power? 1/2. And what's 3 times 1/2? 3/2. So we were right. Now I'm going to plug in 2. 3 times 1/2 to the second power. What's 1/2 to the second power? 1/4. And what's 3 times 1/4? 3/4. So we see we're getting smaller, smaller, smaller. Now let's plot these points. This is where it's going to get weird, okay? We already plotted this point, -1/6. 0, 3. Boom. What do we normally call that point when we're talking about linear functions? The y-intercept. Okay? So off to the side, we're going to write y-intercept equals initial value. Which we already know this, right? From unit rate, word problems, all that good stuff. And let's think about this, right? Anytime I plug 0 in for that exponent, that's going to cancel out my common ratio in the middle, and that just leaves me with that number in front. Look at that. My y-intercept is 3. I had the 3 in front. I'm starting to think this 3 might be my y-intercept. And we said that number in the middle was my common ratio. Again, we're going to break that down more tomorrow. Today we're just plugging in points, or plugging in numbers, plotting points. This is where it gets difficult, right? My next point that I'm going to plot is 1, 3/2. So I'm going to go over to 1. 3/2. How can I write 3/2 as a decimal? 1.5. So in between 1 and 2. Exactly in between 1 and 2. Luckily for us, this y-axis is going by increments of 0.5, so we can do that. 1, 1.5. Does that look like a straight line so far? No, it looks kind of curved. Let's plot this last point. How can I write 3/4 as a decimal? 0.75. So I'm going to go over to 2. I'm going to go not quite up to 1. I'm going to go halfway up to 1. I'm going to make my next point right there. Now I know we're all eager to make a little sloping slide and connect these points, but why aren't we going to do that? Because it's a discrete function, right? If I'm given the domain, I do not want to connect those dots. Okay, we'll take a look at that with the next piece of notes that we get. But for right now, discrete function, it gives you the domain. Think domain discrete. We just want to make those points, but we can clearly see, hey, this is not a straight line. None of these 2 points, or none of these points connect together to make a straight line. All right? Any questions on how we accomplish that? Perfect. Let's take a look at the second one. Second one, my function is f of x is equal to 3 times 4/3 to the power of x for the domain. Now we're going, it's the same domain? No, it's different. -1, 0, 1, 2, 3. So let's plug in -1. 3 times 4/3 to the -1. I'm going to reciprocate my fraction. Multiply by 3. That gives me 9/4. Now, I don't know about you, but when it comes to estimating where a dot's going to be, in my brain it makes more sense to have it as a decimal. So that's what I'm going to do. I'm going to turn 9/4 into a decimal, which is 2.25. That tells me I'm going to go up to 2, and then I'm going to go 1/4 of the way up towards 3. If If you can look at the fraction 9 over 4 and go, I know exactly where that's going to be on the y-axis, great, I'm not judging. At least in my head, decimals make more sense in terms of this. 2.25. Okay, if we went and plotted that point, I'm going to go to -1 on the x. 2, there's 3, so I'm going to be like about right there on the y. Here's my first little point. Now if I plug in 0, again, what's anything to the power of 0? 1. So again, I'm just left with my number that's in front, my coefficient of sorts. It's not really in front of a variable, but it's my number out in front. 0, 3, that one's easy to plot. Right there at 3 on the y-axis. And again, that number in front representing our y-intercept, just like a number 1. What if I plug in 1? What's 4/3 to the power of 1? 4/3. And when I multiply 3 times 4/3, basically what happens with my 3's? They cancel out, exactly. Thank you for that. 3 over 3 is just 1, leaving me with that 4 on the top. 1 comma 4 is my next point. And remember, when we were talking about geometric sequences, the way we find the common ratio is by taking the second term in the sequence and dividing it by the term before it. Right? So here, if I take 4 and I divide it by 3, well, hey, again, that gives me that number inside the parentheses, 4 over 3. Right? So the number in front, there's my y-intercept. That number inside the parentheses is my common ratio. It's kind of like slope, a little bit different, right? Not consistent. What if I plug in 2? What's 4/3 to the power of 2? 16 over 9. I square the top, I square the bottom. Now here I got to multiply 3 times 16, which gives me 48 over 9. Right? We want to leave that bottom number the same. Can I simplify 48 over 9? Nope. 48 divided by 3. Oh, we could. Yeah, we can. 16. But then we'd end up with 16 over 3. So we could do that. Or I could say 5.33. With a little bar on the top because it goes on forever. So for this point, I'm going to go over to 2 on the x-axis, and I'm going to go up to 5, and then I'm going to go 1/3 of the way past 5 on the y-axis. This will be a fun one. Third power. 4 over 3 to the third power. Well, what's 4 to the third power? 4 times 4 times 4? 64. And what's 3 to the third power? 27. So 3 times 64 should be 192?
Yeah, it is. Over 27.
Over 27? Again, I look at my y-axis. I don't know where 192 over 27 is. I'm sorry. Yeah.
You can simplify it.
Yeah, we can. I'm just going to divide it because I want a decimal anyway. 192 over 27 gives me 7.11 forever. So for this point, I'm going to go over to 3. I'm going to go up to 7. And I'm going to go slightly past 7. Again, it's not going to be exact. There's my last point for that one. So again, you'll notice that these points do not form a straight line, but we also do not want to connect them yet because we are just evaluating this function at the domain -1, 0, 1, 2, and 3. Nothing in between. So that's what that discrete graph would look like. Anyone remember how we can tell if this is just in general, if it's a function or not? Yeah, Ava, what can we do? Vertical line test. That's right. If I take my ruler here on the left side and drag it all the way across the right, is there any point where there's two dots directly above each other? No. So this is a function. Before we were talking about linear functions, straight lines. Now exponential functions are going to look like a slide. Anyone ever been to like a water park before?
Yeah.
Ever been on like a super steep water slide? No, maybe. You guys know what I'm talking about?
Yeah.
Like this one?
Yeah.
I went down there before.
That's what our exponential graphs look like. It's like a little, little slide.
I broke my nose on one of those.
Very nice. Are you all right? I think he's fine. All right. Last but not least for this page, number 3. Give this one a try on your own. You guys can do it. You're smart kids. Give it a try. Evaluate. Again, don't connect the dots. You've got 5 inputs. Put them in. Reciprocate where you need to. We'll take like maybe 3 minutes. Whoa, what was that? Did you guys hear that?
Yeah.
3 minutes and 5 seconds.
These look kind of difficult.
There we go.
Me.
Give me a thumbs up if you got through that. Perfect. Let's take a look. So I'm going to plug in -2, 4 to the 3/2 power to the -2. I'm going to flip that around 2/3. I'm going to square it 4/9. I'm going to get 16/9. What's 16 over 9 as a decimal? 1.77 forever. So -2, 1, about 2/3 of the way up. Next one, -1, 3 over 2 to the -1. I flip it around, give me 2/3. Multiply 4 times 2, that gives me 8/3. And that's what, 2.6? Yeah? 66666. 2.6 right there. If I plug in 0, my fraction in the middle goes away. And 4 times 1 just gives me 4. That doesn't seem right. Did I do something wrong? Oh, I went way too high up with that one. There we go. If I plug in 1, I get 12 over 2. What's 12 over 2? 6. That one's not too bad. And if I plug in 2, what's 3 over 2 squared?
9.
9/4. My 4's cancel out, leaving me with 9. There's our little slide. Do I want to connect the dots?
No.
Nope, because this gives me a domain of only 5 points. There's no domain at all. We'll connect our dots. That's what we're going to look at right now. Yeah, there's more. Okay. So double check, make sure yours looks just like that while you're gluing in this second page.
It's literally the same thing. Bro.
Yesterday was easy, so today has to be twice as much work. That's a great guess. You're right.
It better be the worksheet. That's the worksheet right there.
There's only like 6 problems on a worksheet.
It just blows the Just keep on clicking on it. Every shot you just there's like 16 right now.
Take a look in the second time and do it together.
I don't care. Just use it all.
You won't know if I use it all.
I know, but still, just for good measure.
Calculator would be nice. All right, let's get it started so we can get through it. Same idea. Only difference is my 4 is not in parentheses. It's the same thing, right? What's that? Okay, just flip it around. All right, with number 1, f of x is equal to 1/2 times 4 to the power of x. I do not have a domain here, so this is going to be continuous. Now, yes, there are inputs already in the table, But we could plug in any numbers we want, right? These are just the 5 that are going to help us out the most in terms of understanding what the shape of this exponential function is going to look like. So continuous just means we're going to connect the dots at the end. Let's start with -2. If I have 1/2 times 4 to the -2, well, what's the reciprocal of +4? Not -4. 1/4. Right? We flip it around. What's 1/4 squared? 1/16. And what's 1/2 times 1/16? 1/32, which as a decimal is 0.03125. Basically 0, but not quite. Can you see that? No, you cannot.
Yes.
0.03, we'll just call it 0.03. Okay, almost 0. Pretty darn close to 0. Let's plug in -1. 1/2, 4 to the -1. I'm just going to flip it around and get 1/4. What's 1/2 times 1/4? 1/8. 1 divided by 8 gives me 0.125. Getting closer to 1, further away from 0. If I plug in 0, my 4 goes away. Right? What's 1/2 times 1? 1/2 times 1? 1/2. Or 0.5. 3. If I plug in 1, what's 4 to the first power? Just 4. And what's 1/2 times 4? 2. Finally, I plug in 2. What's 4 to the second power? 16. And then what's half of 16? The heirs are 8. All right, 5 points. Let's plot them. I'm going to start with the easy ones. 2, 8. 2, 8 all the way up there. 1, 2. Much lower. My y-intercept at 0, 0.5, which is right there, about. And then I've got -1, 0.125. So -1 and almost close to 0. Okay, not on the x-axis, right? If we're on the x-axis, then it's 0. What are you guys doing? Anthony, come sit at the side table over here, buddy. Thank you. And my last point, -2, 0.03. Again, very close to 0. Not quite exactly 0. All right? So here we see a real steep drop off of this slide. And we're going to connect our dots as best we can. Now, here's what we're going to do. I'm going to start where we're close to 0. So I'm going to go over here. I'm going to do this little line. I'm going to connect them all, making it as curved as we can. And I want arrows on both ends. You guys kind of see the slide I was talking about? Yeah. So with exponential functions, we could be sliding down to the left, sliding down to the right. We could have an upside down looking slide, which we'll talk about, I don't know, Thursday or something like that. Okay, and we know we're going to have something shaped like this when my x is an exponent, right? That's what gives it away. That's why it's an exponential function, because my x is my exponent. And that's what we get right there. Give me a thumbs up if that makes some sense. That seems not too bad. Okay. Perfect. Now, this bottom line, we don't want to go through the x-axis. It's going to look like a flat line when we get down to this point. It's technically not, but with the the space that we have and our eyes being the way they are, it's going to look like a flat line. But we got to remember, technically, it's not a flat line. All right, let's take a look at the second one. Again, there's no domain, so this is going to be continuous. And here the values I get are 0, 1, 2, 3, 4, 5. All right. So if I plug in 0, what's 1/3 to the power of 0? 1. 9 times 1 gives me 9. I plug in 1. I get 9 times 1/3. What's 1/3 of 9? 3. I plug in 2. I get 9 times 1/9. What's 1/9 of 9? 1. Are my outputs getting bigger or smaller? Smaller? How much smaller? By a third. Exactly. We're just dividing the previous output by 3. Again, that number inside my parentheses, that's my common ratio. If I plug in 3 now, this is going to get messy. What's 1/3 to the power of 3? 1/3, yeah, 0.33, yeah. But 1/3 to the power of 3, 3 times 3 times 3 gives me 1/27th. Oh, I see what you're talking about. Yeah. And then 9/27ths gives me 1/3, or what'd you say, Davis?
0.33.
Perfect. Plug in the power of 4. What's 27 times 4?
81.
81. So it gives me 9 over 81, or 1/9. 1 divided by 9 is 0.111 forever. And when I plug in 5, 81 times 5.
243.
243?
Yes.
Or not 81 times 5, I'm tripping. 81 times 3. Yeah, 243. I get 9 over 243, which is 1/27th. And 1 divided by 27 is 0.037. Basically 0 again. Did I get, is it not 7?
Yeah, it's
No. We just need to know it's very close to 0. That's really it. Okay? Now I'm going to plot these points. Again, the first 3 are easy. 0, 9, 1, 3, 2, 1. We see our slide going down towards our x-axis. Then I've got 3, 1/3, 4.11, and 5.03. And there's my graph in red. Again, this isn't really an exact science because we're estimating where the points are. We're estimating how that line goes through it. But as long as you're close enough and you've got all your numbers right, that's what matters. Okay, if you're all good on number 2, try number 3. Give it a shot. Take another 3 minutes, and then we'll get started on the homework. thumbs up. You got through that third one. Anybody? Okay, take another minute. Finish up. Mm-hmm. All right, last but not least, number 3. Let's check it out. 6 times 2/3 to the -1. Again, -1 just tells me I'm going to flip my 2/3 into a 3/2. I multiply my big number across the top. 6 times 3 gives me 18. I keep my number on the bottom the same. And what is 18 divided by 2? 9. No calculator needed there. Okay, if you have a calculator, well, never mind. We plug in 0. What's anything to the power of 0? 1. What's 6 times 1? 6. Plug in 1. 2/3 to the power of 1 is just 2/3. Again, I multiply 6 across the top. 6 times 2 is 12. Keep my bottom the same, which is 3. And what's 12 divided by 3? 4. Hey, we might get out of here without having any decimals. I'm kidding. I know it's not going to be decimals. Plug in 2. What's 2/3 squared? 4/9. Okay, I'm going to multiply the 6 times the 4. That gives me 24 over 9. 2.666 forever. Plug in a 3. What's 2/3 cubed?
8/27.
8
27.
27ths. 6 times 8 is what, 48? 48 over 27. Boom, 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 boom. 1.77 forever. Then I plug in a 4. What's 2/3 to the 4th power? 16 over 81. Multiply the 6 across the top. 96 over 81. And 96 divided by 81 is 1.19. So we're getting smaller and smaller, right? -19, that one's easy to plot. 0,6. 1,4. So far, so good. 2. And then 2.6 is like right there-ish. 3 and 1.77 is like right there-ish. And 4, 1.19 is about right there. Bit smaller. Now, unlike the other ones, we don't really get all that close to 0 here, correct? So what if I plug in 7? Let's see. If I plug in 7, I get 6 to the 2/3 to the 6 times 2/3 to the 7th power. Well, 2 to the 7th power is 128. 3 to the 7th power is 2187. Again, we're just using a calculator here. Multiply across the top to get 768 over 2187.
0.351.
Perfect. We'll just Correct. Thank you. We'll just cut it at 2. 0.35. So 7, 0.35, like a third of the way up there. And then that kind of fills in our gap, right? Because what a lot of people will do at that point is make this little curve, and then when they hit this point, they'll just make like a flat line, and it'll be way too high up. We want to hit this point down here too before we descend towards 0, just like that. That slide doesn't look as scary. This is going to take some practice, though, right? It's kind of tricky. We just spent 45 minutes talking about it. It's like our longest notes ever, I want to say, but